Hey everybody, sorry for cutting off the last video. I meant to pause it and for some reason or other it didn't pause. So you all had the thrill of seeing me piddle around on the board for a few minutes. And then when I resumed filming, so to speak, I in fact actually cut off the video. One of these days I'll make it into the 21st century, but it doesn't look like it's going to happen today. At any rate, here's where we left off. We had this inequality, or this string of inequalities. And what we noted was that a sub n is less than or equal to its successor, a sub n plus 1. And so that means that the sequence of left endpoints is monotone increasing. But there's something else going on here too. For every natural number n, a sub n is less than or equal to b sub 1. So this sequence of left endpoints is monotone increasing, and it's bounded above by b sub 1. So by the monotone convergence theorem, which we'll call the bounded convergence theorem, the sequence of left endpoints converges to its least upper bound, and we're going to call that least upper bound A. So this sequence of left endpoints converges to its least upper bound, which we call A. Now let's go back to our string of inequalities here for a minute and notice that each term, b sub n plus 1, is less than or equal to its predecessor, b sub n. So the sequence of right endpoints, b sub n, is monotone decreasing. And not only that, for all natural numbers n, b sub n is greater than or equal to a sub 1. So this sequence of right endpoints, b sub n, is monotone decreasing, and it's bounded below by a sub 1. So by the monotone convergence theorem, or the bounded convergence theorem, this sequence of right endpoints converges to its greatest lower bound, and we're going to call that greatest lower bound B. So this sequence of right endpoints converges to the greatest lower bound of this sequence that we're going to call B. And let's see, I was going to say I'll let the cat out of the bag, but I'm going to let one of the cats out of the bag. It's our intention to show that A and B are equal. In other words, the least upper bound of the sequence of left endpoints and the greatest lower bound of the sequence of right endpoints are one and the same thing. Now, let me see if I can pause without shutting this off. Maybe I should mention one other thing before I erase all of this. I did say that it's our intention to show that the least upper bound, rather, of the sequence A sub n and the greatest lower bound of the sequence B sub n are actually one and the same thing. And we'll name this common value P. In other words, A and B are equal. We're going to show that A and B are equal. And that common value of A and B, we're going to name that P. So just something to keep in mind as we proceed. Okay, we're back. And our objective is to show that A and B are equal. A, the least upper bound of the sequence of A sub n's, and B, the greatest lower bound of the sequence of B sub n's, are equal. So we start off by saying, let epsilon greater than 0 be given. And in order to show that A and B are equal, we make some preliminary observations. First of all, since the sequence A sub n converges to A, there's some natural number capital N such that little n greater than capital N implies that A sub n minus A is as small as we want to make it. Could be epsilon or epsilon over 2, but however small we want to make this difference, we can make it that small. Secondly, since the sequence B sub n converges to B, there's some natural number n, capital N, such that little n greater than capital N implies that the difference between B sub n and B is less than whatever, epsilon, epsilon over 2. However close together we want to make these things, we can do that. And then finally, since the limit of B sub n minus A sub n as n goes to infinity is 0, there's some natural number n, capital N, such that little n greater than capital N implies, whoops, not what I wanted, B sub n minus A sub n is less than epsilon or epsilon over 2. We can make B sub n and A sub n as close together as we want. Now you're looking at this and you probably are thinking that I have done something very short-sighted. You're absolutely right. The natural number capital N here, such that little n greater than capital N will force A sub n and A to be less than whatever, may not be the same capital N here, such that n greater than capital N force B sub n minus B to be less than whatever. And whatever these two n's are probably not going to be the same as the capital N here, such that little n greater than capital N forces B sub n and A sub n to be a certain distance, no more than a certain distance apart. So, I'm going to have to do this. Since this capital N is in reference to the sequence of A sub n's that supposedly converges to A, I'm going to call this capital N sub A. And since this capital N is made with reference to the sequence B sub n that we're trying to show converges to B, I'm going to call this capital N sub B. And then, since this capital N has reference to the difference of B sub n and A sub n, for lack of anything better to call it, I'm going to call it capital N sub AB. So I've eliminated some of the ambiguity here. And let's see, just exactly how close do I want A sub n and A to be? How close do I want B sub n and B to be? How close do I want B sub n and A sub n to be? It turns out that if I make each of these smaller than epsilon over 3, everything will work out wonderfully and we'll live happily ever after. Now, I want this to be true, I want this to be true, I want this to be true. So my little n has to be small enough such that all three of these conditions are satisfied, which means essentially that I'm going to have little n greater than this thing, and little n greater than that thing, and little n greater than this thing. So here's what I'm going to do. Here's where my capital N comes in. we'll let capital N be the largest of these three values. We're going to let capital N be the largest of these three values. So if little n is greater than capital N, then little n is also greater than each one of these things, which means each one of these conditions is going to hold. Now wonderful things are going to happen, I hope. We'll find out in just a minute. We're back. And for n greater than capital N, we have b minus a equals something. Well, you know what? In our observations, we had bn minus an less than epsilon over 3. We had b minus b sub n less than epsilon over 3. Or maybe it was b sub n minus b less than epsilon over 3. And we had a minus a sub n less than epsilon over 3. Somehow, I'd like to relate b and a to one another, but I can't relate b and a to one another because a is only in reference to a sub n, and a sub n has reference to b sub n, and b sub n has reference to b. But b and a, you know, one's the greatest lower bound, the other's the least upper bound. And I don't really know how they relate to one another. It would be nice if I could get an a sub n in here or a b sub n in here so that I could at least relate a and b to something that I know something about. So how on earth am I going to get an a sub n in here or a b sub n in here? Or maybe both. Now, if you're thinking back to real analysis 1 and thinking, well, we can just add an a sub n and then subtract it right back, and we can add a b sub n and then subtract it right back, then you learned well in Cal 1, in real analysis 1. This is exactly what we're going to do. We're going to introduce a sub n and b sub n into this absolute value by inserting a sub n and b sub n and then subtracting a sub n and b sub n right back. I won't say it's the oldest trick in the book, but it may be the most undervalued trick in the book. We use this a lot. It's a simple trick. It's a cheap trick, but it's very valuable, and we're going to do it right now. So I have my b, and I'm going to subtract b sub n and add it right back. And then I'm going to subtract a sub n, and then I'm going to add it right back. And I already have negative a in here. So I've really committed no foul. This is 0. This is 0. So I still have b minus a and nothing else. But somehow I've introduced my b sub n's and a sub n's into this inequality. And I'll group these as follows. B minus b sub n plus b sub n minus a sub n plus a sub n minus a. Oh, heavens to Betsy, what should I do now? You smell something? I think I do. I smell the triangle inequality coming up. That's exactly what it is. This thing is less than or equal to the sum of the corresponding absolute values. And I'll just switch the terms around here to make it more aesthetically pleasing. That's better. B sub n minus b. And oh my goodness, we know what all three of these things are. Less than epsilon over 3, less than epsilon over 3, less than epsilon over 3. And can we see that? Yeah, I guess we can. Now, what does this accomplish? If we look at what we started with, b minus a, absolute value, we have b minus a less than epsilon, where epsilon is an arbitrary positive number. So in other words, this has to be true for all positive values of epsilon. This difference, the absolute value of b minus a, is less than epsilon for all positive values of epsilon. So can b minus a be positive? No, because if the absolute value of b minus a were positive, we could call that epsilon. But then it turns out that b minus a, according to what we proved, is less than epsilon for all positive values of epsilon. So in a sense, if we assume that b minus a is positive, we're claiming that b minus a is less than or equal to its, we're claiming that b minus a is less than itself. And that can't happen. So b minus a absolute value is less than epsilon. That implies that b minus a absolute value is 0, which means that b minus a is 0. And that means that b equals a. And this common value of a and b, we call it p. So p is equal to a, and what was a? A was the least upper bound of this sequence a sub n. So that means that a sub n is less than or equal to p for all natural numbers n, because P is the least upper bound of A sub n. And we can also reason the same way with B. P is equal to B, which is the greatest lower bound of the sequence of right endpoints B sub n. P is the greatest lower bound of that sequence, so that means that P is less than or equal to B sub n for all n in capital N. P is greater than A sub n for all natural numbers n. P is less than or equal to B sub n for all natural numbers little n. So P is sandwiched in between A sub n and B sub n for all natural numbers n. And that's the same thing as saying that P is an element of this interval, A sub n, B sub n, for all natural numbers little n. Well, you know what? If P is in every one of these intervals, it's got to be in their intersection, right? So it looks like we're done, but we're not quite. We have proved that there's this point P that's in the intersection of all of these intervals. But our statement of the nested interval theorem actually had a little bit more than that to say. The nested interval theorem also says that this point P is unique. In other words, there's only one real number P in the intersection of these intervals, and this is it. So we have a little bit more work to do yet. We have to show that this point P is unique, and that there can't be any other real number in this intersection. Now we show that this point P is unique. For if we have any real number Q where Q is not equal to P, there are two possibilities. Either Q is less than P or Q is greater than P. So let's look at the first case. If Q is less than P, then for some natural number K, A sub K is going to have to be greater than or equal, no, just greater than Q. Now, why is that? If there's no natural number K such that A sub K is greater than Q, then A sub K is less than or equal to Q for all natural numbers K. Let's see, A sub K is less than or equal to Q for all natural numbers K. So what does that tell us? That means that Q is an upper bound of this sequence A sub k. Okay. So if all of the terms of the sequence are less than Q for every natural number k, this would mean that Q is an upper bound of the sequence. Yeah, so what? Big deal. But wait a minute. We're assuming that Q is less than P, and P is the least upper bound of the sequence A sub k. So this would mean that Q is an upper bound of the sequence that's less than P, and let's make this a comma. But that contradicts the fact this contradicts the fact that P is the least upper bound of this sequence. So what have we shown? Given Q less than P, there exists a natural number K such that A sub k is greater than Q. Yeah, okay, so what? Oh, I know what. If A sub k is greater than Q, then Q is not going to be in the interval A sub k, B sub k. And that in turn implies that Q is not in the intersection of all of these intervals. Okay. Yeah. So take any real number Q where Q is not equal to P. And either Q is less than P or Q is greater than P. If Q is less than P, then Q fails to be in one of these closed intervals, which means that Q is not in the intersection of those nested intervals. And now we look at the case where Q is greater than P. And I think that's what I want. And dot, 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 this would imply, whoops, whoops, whoops. Hold on just a second, let me rediscover my brains. I don't think I really want to reproduce this whole argument. Oh, what the heck, maybe I will. Okay. Now, what problem are we going to run into? Let me erase the board and make more room, and we'll get right to it. Okay, I rediscovered my brains. I apologize. Let's follow this train of thought, but I'm going to have to change something. And here's what I'm going to have to change. Make that B sub k. So if we assume that Q is greater than P, there exists a natural number K such that B sub k is less than Q. Why is that? Well, otherwise, B sub k is greater than or equal to Q for all natural numbers K. See, if it's not true that for some natural number K, B sub k is less than Q, that means that B sub k is greater than or equal to Q for all natural numbers K. And this means that Q is a lower bound for this entire sequence. If B sub k is greater than or equal to Q for all natural numbers K, then Q is a lower bound of this sequence. Yeah, so what? Well, that would mean that Q is a lower bound of B sub n that's greater than P. See, we assume that Q is greater than P. So what's the problem? This contradicts the fact that P is the greatest lower bound of B sub n. So if we assume that Q is greater than P, then there has to be some natural number K such that B sub k is less than Q. So what does that mean? That means that Q is not contained in this interval, A sub k, B sub k. And that means that Q is not in the intersection of all of these intervals, A sub n, B sub n. So if we assume that Q is less than P, Q is not in this intersection. If we assume that Q is greater than P, Q is not in this intersection. So the only real number that can possibly be in this intersection is P. And that means that P is unique. So that finishes our proof. Next time, we will look at one of the big theorems of math, the Bolzano-Weierstrass theorem. And we will also look at limit points of sets of real numbers. Not necessarily limits of sequences of real numbers, but just limit points of non-empty sets of real numbers.